So now we're going to talk about 2 and 3-dimensional motion. And when we move from vectors, and the whole idea behind vectors is that we want to be able to deal with the independent coordinates. So when we do that, and in general physics, what we're going to talk about are some special cases. We start out with learning the concepts where we're going to deal with constant acceleration. Now, when we get to things that are higher level, like dynamics and mechanics and things that are up further, we can have a variable acceleration. But for right now, we're going to stick to a constant acceleration because it helps us learn the concepts. And when we do that in 2 dimensions, we're going to get that special case that we call projectile motion. So here we go. We're going to start looking at our 2 dimensions. So remember that we started with a position vector, and we talked about that in vector notation where we have an I component, a J component, and a K component. I, J, and K are unit vectors in the X, Y, and Z coordinate systems. And we can write that position vector. So we know our position, at least in the Cartesian coordinate system, can be represented as this R, I, J, and K. We also know that when we change R with respect to time, so anytime you see a WRT in a math book or a physics book, we're talking about with respect to time, we know it's going to be a velocity vector. And because of where we are in our mathematics and in our training, we're going to look at it both from the change form or our delta form. And in engineering physics, we also want to know that that's our derivative form, that we can get our velocity is our derivative with respect to x in terms of time, our derivative with respect to y in terms of time, and our derivative with respect to z in terms of time. Our acceleration is our change in velocity. So we're going to get that x component of the velocity, that y component of the velocity, and that z component of the velocity, or we're going to see that it's a second derivative. So I know where we are right now in terms of what we're doing, but I want you to see that calculus version of the equations. But the key point here is that the X, Y, and Z are independent motions. And we're about to see that really, really clearly, that those are independent motions. So as we saw before in our 1-dimensional motion form and in our 2-dimensional motion form, we know that we have our kinematics toolkit. And we've seen these kinematics equations. In fact, I've actually asked you to derive these equations based on what you see in the textbook. And we know that we can rewrite these in terms of our velocity in the x direction, which we can use that subscript of v of x, the velocity in the y direction, which we can use that subscript of v of y, and our velocity in the z direction, which we can use that subscript v of z. Now you will have to account for the acceleration in each direction. You have to account for the velocity in each direction, but we can rewrite in our Cartesian coordinate system based on those components. And we saw that back in the vectors when we were just dealing with vectors in and of themselves. We saw that we could do that projection on the y-axis or that projection on the x-axis, but we know that I can get to this point by going over here and up here, or I can get to that same point by going up and over. So we can do those independent motion equations. So let's think of our ball. When we roll it across the floor, we don't necessarily have an acceleration associated with it. Now, if I'm in a car and I'm accelerating from a stop sign, we're going to have an acceleration. But when I toss the ball up in the air and it comes back down, we do have an acceleration acting on the ball, and that acceleration is the acceleration due to gravity. So we can rewrite our kinematics equations up here in terms of our x components, whether it's the x component in velocity, the x component in the acceleration, or we can redo this in terms of our y components. We want to have that key point that the x and y are independent motions. So let's look at a ball tossed in the air. Now we did it straight up in one-dimensional motion, but this time we're going to allow the ball to travel. And I used our video analysis software, and we can plot the position of our ball in terms of its X and Y components. And we get this nice parabolic travel. So we're going to start to see what we know familiarly as projectile motion. But I want to look at this and show you that the X and Y component are independent. So we've plotted this position, but now we've used our video analysis software to plot the Y position versus time and to plot the X position versus time. And sure enough, because we have no acceleration in the X direction, we're going to get that X is equal to the velocity in the X direction times time. And there's no acceleration component. So if we go back to our kinematics toolkit here, we're looking at our velocity with respect to time, or we're looking at this part right here. Let's look at this equation right here, that our change in X is equal to our initial velocity in the X direction times time. And because there's no acceleration in the X direction, that part of the component ends up being equal to 0. We don't have to worry about that part. So when we do that, we're going to get a straight line. It's traveling at a constant velocity. That's not the case in the Y direction. In the Y direction, we do have that acceleration due to gravity. And we're going to get this nice quadratic equation. Going back to our toolkit, if we write this in terms of Y, our change in Y is going to equal our initial velocity in the Y direction times time minus 1/2 gravity, because gravity's in the Y direction and it's facing downward, times time squared, and we see that it's a quadratic equation, and a quadratic equation is going to give me a parabola. So it's really clear to see in a real world example that our X component is independent of what's happening in the Y component. And if we look at it in terms of our vector analysis, we can take that same parabolic action, understanding that the distance between here tells me how much further it moves, and we can get our resultant vector. So we can get our position vector, our change in position vector. It's going to be our change in X, our change in Y, and our change in Z. Even though we're showing a picture in just 2 dimensions, it's going to happen in the 3 dimensions. And we know our velocity is going to work out that way. And we get our instantaneous velocity, and we get our individual velocity components. So in the horizontal motion, because we have no acceleration, I don't get an acceleration term, but in the Y component, I do. And when we go back and we look at our picture here, we get the velocity, initial velocity in the X direction is related to the cosine of this angle. Remember that projection, right? That projection on the X direction. And we get our Y component that we can rewrite our components here, where we have our initial component in the X direction and our initial component in the Y direction. And we can find the mathematic equation for that motion of the projectile. We can do it in the same terms in terms of acceleration. Our acceleration's only in the Y direction. We can rewrite our velocity. Here's our velocity in the X direction. Here's our velocity in the Y direction. And we can look at it in terms of our changing components. So this right here is just rewriting our kinematics toolkit in understanding of how that motion is occurring. Now I want to bring this up a little bit because in the way our CATS textbook does it and the way a lot of other textbooks do it, we're going to talk about circular motion. And circular motion is very, very important in physics because we're going to be able to accommodate a variety of things. So we're going to introduce a circle, and we're going to do it here right now, that I'm traveling around a circle at a constant speed. Now at a constant speed, that means this velocity vector is all going to have the same magnitude. And we know that acceleration is a change in that velocity vector with respect to time. Even though we're not changing the magnitude, we are changing direction. So we are going to get an acceleration. And as we go around in a circle, that's going to be a center-seeking acceleration. And that's what we call our centripetal acceleration. That center-seeking is a centripetal acceleration. And that's what we ultimately get that deals with gravity on the planets because of planetary motion. But we get that centripetal acceleration. And we're going to see later on that we're going to have a tangential component of that acceleration as well. So we're going to get two aspects of this acceleration, but for right now, we're going to look at that center. And if we think about this unit circle, we can write x at any point of this circle based on that, where it is with our angular frequency times time. And we're going to see this over and over again. We're going to see it later on in the semester, and we'll certainly see it when we start at the beginning of Physics 2, that this omega is that angular frequency, and we're going to want to find out how fast things translate around the circle. So we want key things here. As I'm traveling around my unit circle, I will have an x component and a y component, and I can translate back and forth between my polar coordinate system and my Cartesian coordinate system. And we're looking at that change in the angle with respect to time. It's going to have a lot to do with that angular frequency. So we start to see that. So let's talk about this unit circle, because the unit circle is really, really important. Circular motion is just another representation of two-dimensional motion. And as we go through that, we can draw a triangle at any point along this circle. And we can have an x component and a y component, and we can come up with whatever the radius is of that circle. That's where this A is. And when we start talking about wave motion, that A is going to represent the amplitude of our circle. Then we can look at this unit circle going back and forth, and we can calculate that amplitude based on its x component and y component. So as I go around this circle, I'm going to move back and forth across the x-axis. As I go around the circle, I'm going to move back and forth across the y-axis. And we can look at that in terms of its angular frequency. So let's go on a little bit further. So going back, we can convert between our polar coordinates and our Cartesian coordinates. Remember that our x and y can be represented by our r cosine of the angle and our sine of the angle, so that we can look at it in terms of those polar coordinate system. And so anywhere on that circle, I'm going to have my right triangle. And we can use that Pythagorean theorem to show that y is equal to r sine theta, x is equal to r cosine theta, and we can figure out the angle based on using that tangent function. So that really is going to help us out moving on. So one of the things we do want to talk about is the speed at which we travel. So if I'm starting with that second hand problem, I've got the clock going around the second hand, which we've already seen. We've already used that minute hand. That if I move through this arc length S, all right, that's my arc length formula. It's going to be related to whatever my R is. How far away from my origin am I? And our angle theta. We can do that. Initial velocity is the change in S with the change in time, and we know that S is equal to theta R, and we come up and we can convert the velocity in terms of that angular frequency. So we can go back and forth. And the thing here is that my angular frequency is also related to the period. The period is the time that it takes to make one complete cycle. So if I'm traveling around in a circle, it's the time that it takes for me to travel around that entire circle. And we know that the circle is equal to 2 pi. So I can actually look at that and I can calculate the angular speed. A key point here for when you're working in your calculator. This is going to be in radians per second. All right. We're not in degrees per second, we're in radians per second. And that's really, really important because if I'm dealing with a frequency, my frequency should be 1 over time. So 1 hertz is equal to 1 over seconds. So my frequency should be there. And typically what happens when we're dealing with radians, we don't write down the fact that a radian is there. We end up writing this as 1 over the seconds. So looking at this, we can kind of go out and we can get our centripetal acceleration. That's the center-seeking acceleration. We can look at our R in terms of our angular frequency. We can look at our acceleration in terms of our angular frequency, and we can figure out our centripetal acceleration. And then converting that back into our Cartesian coordinate system, we get our V squared over R. And we'll see this over and over again as we move something around a corner, or we're talking about a banked curve, or we're dealing with NASCAR, or you can use the centrifuge that you see here. This is the NASA centrifuge in order to recreate gravity on different platforms to measure the effects of acceleration on humans. We can do that part. So that starts looking at the two-dimensional motions, but there's one other case that we need to talk about that's a special case as well, and that's dealing with relative motion. And relative motion is that motion that we look at from different points of view. So think about the fact if I'm on a train and a person is standing at the intersection watching the train go by, and if I'm walking forward in the car, how I look, or my motion relative to the person that's standing on the corner, looks like I'm walking faster than the train. We do a lot of this in terms of the boat or submarines. So if Hannah's sitting here and watching Aaron move away on the boat, and if he's walking on our boat away, he's going to actually look like he's moving faster than the boat from Hannah's point of view. So we have to look at that. Similarly, how he looks where the motion of the submarine is coming forward, he looks like he's moving a heck of a lot faster because both the submarine is moving towards Aaron and Aaron's moving towards the submarine. We're going to be able to see it. So we look at how we're going to represent this and dealing with respect to. So the position with respect to our person, or with respect to the land, or with respect to the ship, is going to be very important. We can quantify it. We can look at that particular portion of it. We can take the derivative and find a relative velocity, and we could do the same thing in those acceleration points of view. So we can look at that motion, deal with that motion, and we can have that aspect there. So I will put up a couple of example problems, but this should get you started and get you the theory that's behind the stuff in our two-dimensional motion and our three-dimensional motion. When we bring in the third dimension, we're just actually bringing the X, Y, and Z components. And I just want to make sure that you understand how we can relate that and how it all works out. But most of our problems are going to be in that two-dimensional motion case, and that's projectile motion. Remember, projectile motion is a special case. We're making the assumption that acceleration is a constant against the surface of the Earth, and so we can look at it from that perspective.